It's now started. So now we're going to start talking about regression. And early on, we were talking about just means or averages. And if we're looking at how much time people spend in the hospital, and we're looking at somebody that has, this is a longer time than this time, and we're to say, hey, wait a minute, this is the amount of days on average, somebody that had antibiotics and a breathing treatment. This is how many days somebody stayed in the hospital that just had a breathing treatment. And this is how long somebody stays in the hospital that is just using antibiotics. And this is somebody with relatively no type of intervention. We're just watching them at the hospital. And these are just solid numbers. These are just averages, means. Now, what happens if you say, hey, wait a minute, what happens if we increase breathing treatments? Would that decrease the amount of time? So what we're trying to see is is there a linear relationship between that? So imagine if we start to say, hey, wait a minute, with our independent variable and our dependent variable, this is the amount of days. This is 0 days. Up here, perhaps 100 days. This is 0 breathing treatments. Perhaps this is 100 breathing treatments. And as we increase our breathing treatments, so that number is increasing, the amount of days that they're staying is actually decreasing. And we can see that right here. If we're up to 50 breathing treatments, perhaps their days is at like 10 days. And so we see as we increase the breathing treatments, the days are going down. And we notice that there's a linear relationship between that. And so what regression does is it's testing to see that if you increase one, does it either increase or decrease this one? And these data points that create a slope, these data points, if we link them together, it creates a slope. And that slope is referred to as a beta. That slope is called a beta. Okay, and that slope can actually have a value to it. And that slope can say, hey, every breathing treatment decreases the amount of days that they stay by 10 days. And we're like, oh, okay, well, if we increase breathing treatments, it allows them to stay less days. How much per breathing treatment? That's the value of that beta or that slope is what it's telling us. And we're like, that's pretty good. So now all we need to know is like how many breathing treatments we're going to give them. And this will decrease from the average amount of days that they stay. On average, person staying like 75 days. Every breathing treatment, they stay 10 less days. And so we can then begin to calculate what's the average amount of days that they will stay per breathing treatment, right? Plus or minus some type of error that's in this model, because the data is not perfect. They have to have some error. It has to be off by a certain amount. And that's what we're calculating here. We start off with the base. Every breathing treatment minus 10 days. How many breathing treatments are we going to do? And that tells us the amount of days they'll stay. So far, so good. Any questions so far? Okay. So when we're checking these betas.
Sorry, one question. Which is,
sure.
Is Y or X dependable?
So the Y, this is dependent and this is independent.
Okay.
Which means that breathing treatments affects the amount of days.
Okay.
But the amount of days that they stay doesn't affect the amount of breathing treatments they have, right?
Yeah,
Definitely,
yeah.
if you increase the breathing treatments, the days go down.
Okay.
That's what it's saying. Okay. So now when we start to look at regression model, the regression model tells us a couple different things. One, we have an intercept, right? So in our regression model, we have an intercept and we call that B0. And then we have our slope and we call that B1. And from that slope, we have data points. And when we look at this slope, if that slope is equal to like 10 days, what we do is we're able to calculate how many days it should be based off of that, and then look to see how many days it actually is from that slope. And if it should be at this point, where the amount of days should be like 20 days, and we notice that some people are staying like 25 days, we know that some people are staying 5 days over, so there's some error in the model. And so if we can calculate all these errors together and say, hey, on average, the slope appears to be off by about 3 days. That would be our standard error for the overall model. And then when we start doing our calculations, we would say, oh, wait a minute. It should be this amount of days they stay, but whatever our calculations are, they'll be off by roughly about 3 days. Okay, and that's kind of what our regression is looking at. Now, our regression, we want to make sure that after we tell them how many days somebody should be staying, we want to make sure that this slope that we have, because we have our B0, our B1, we want to make sure that this slope, 1, is linear, not curvilinear. Because if it's curvilinear, then it's kind of hard or if it has like this, it's kind of hard to know how we're going to calculate this. It's much easier to calculate it or much easier to come out with some type of number if it is linear. If it's curvilinear and it's different every time, it's hard for us to come up with some type of stable or continuous forecast. And that's why we can't use curvilinear data, because the forecast will always be off.
What's the thing you circle right there? Is that a deviation?
This right here?
Yeah.
That's standard deviation, yeah, standard error. It's going to be off roughly by 3 days, right? And so we have to make sure that that line is consistent. And so our overall model, when we check it, our hypothesis is going to check this. We're going to say, hey, B1 equals 0, B1 does not equal 0. What does that mean? So in the overall model, when we have a regression, if B1 equals 0, this is B1. We don't ask if B0 equals 0, that's the intercept. So our overall model is this like no slope? If you increase breathing treatments, it doesn't decrease the days in the hospital, right? If that's the case, then this entire experiment's no good. Keep on increasing breathing treatments and they stay the same amount of days. That's what this is saying, that breathing treatments have no effect. What this is saying is like, no, it is a slope. And it could be an inverted slope or a regular slope, but it is a slope. And so what we do is we look at our significant F, which is our p-value. Significant F is the p-value. When I say p-value, it's a probability value. And if our significant F or our p-value is below our level of significance, then we can reject our null and say how confident we are that there has a slope. So far, so good. Now, our assumptions are that our p-value is accurate, right? That's one of our assumptions. How do we check our p-value? Normality, right? Skewness and kurtosis checks our p-value. Okay, it's going to be off by this amount. How do we check to make sure that that standard deviation or that standard error is accurate? Oh, our Durbin-Watson has to be greater than 1.3, greater than 1.3. Okay, Durbin-Watson has to be greater than 1.3. We want to check that. We also want to make sure that this line is not curvilinear, that it's actually linear. So we don't want to see in our residuals, we don't want to see curvilinear patterns. If it is, it's curvilinear. And the last thing that we want to check is to make sure that our standard deviation or our error is consistent for the entire model. So what we want to look at is our error. Does it stay consistent? Is this constantly at 3 days or does it increase over time? We want to make sure that our error is consistent. And so what we're going to do is we're going to calculate what we predict and what it actually is. And we want to make sure that we don't see a pie shape. We don't see it increasing over time. That's equal variances. Yeah. And we want to make sure that we don't see it increasing over time. And so when we
Professor,
run,
can you go over again? Because that was a little bit quick for me.
I am. That's exactly what I'm going to do. So I'm going to dig into this one right now.
No, just about the linearity and everything that you, oh, okay.
I'm going to dig into this now. Okay. So now that we've checked our model and we start to forecast, we need to make sure that our forecasts are accurate. If we see a curvilinear pattern, our forecasts are not accurate. So if we see a curvilinear pattern, that variable is not suitable to check, right? So if we see a curvilinear pattern, this or this, we can't use that variable. Now we learned in our assignment that sometimes you can actually do an interaction term and fix it if it's curvilinear or flat. Or you can square or square root the data, but it's fixable. But for the most part, we want to make sure that it's not curvilinear. We also, when we're doing this model and we write up our regression model, the equations when we plug numbers in there. So when we write this up, y equals B0 plus B1 times how many breathing treatments plus or minus our error, right? When we're writing that up, we want to find out, hey, how accurate is our error? That's what this does, our independence. And we use our Durbin-Watson, and our Durbin-Watson, if our Durbin-Watson is greater than 1.3, then our standard error is okay. If it's not, then our standard error, if not, standard error is no good. It's not reliable. Right? Our standard error is not reliable if our Durbin-Watson's below 1.3. And our Durbin-Watson is just like with our ANOVA is, so with the ANOVA, we checked I and E. With the regression, just L is the only thing added. And so the same thing as they're looking at error, right? Normality, again, same as with the t-test.
Professor, so
Go
you
ahead.
would say if the Durbin-Watson is above 1.3, that means the variables are dependent.
No, that means that so if the Durbin-Watson is above 1.3, that means that we are independent, and that means that our standard error is okay in this model.
So it has to be more than 1.3.
Greater than 1.3, yeah.
Oh.
Sorry. The Durbin-Watson has to be greater than 1.3.
Okay.
Sorry. Durbin-Watson has to be greater than 1.3. And if it's greater than 1.3, then our standard error is okay. If it's not greater than 1.3,
then it's dependent.
yes.
Okay.
And so just like with our t-test and our ANOVA, normality is important. Normality, again, checks the accuracy of the p-value. Do you remember that? So normality, remember we're looking at the p-value, we're looking at normality, and we're saying, hey, wait a minute. If it's not normally distributed, the p-value is not accurate. So again, we're looking at skewness and kurtosis, and it has to be between -1 and 1. If it's between -1 to 1, then we're okay. If it's not, then our p-value is inaccurate. What equal variability is looking at is when we have a slope, we're hoping that the standard deviation is staying equal, right? Or if the standard deviation is 3, it's between that, right? We're hoping that it stays equal. But what happens if the standard deviation starts doing that? Where it's not equal over time, it starts increasing. Then when we start forecasting and we say, hey, it should be there, and it should be there, maybe the data is actually down here. So then our forecasts can be off, where we're saying, hey, it should be here, but maybe it's up here, or maybe it's down here. And that's what it's looking at, that because the error is increasing over time, it's throwing our forecasts off more and more and more. And so in the regression model, it looks at the standard deviation as error. And so if the error is increasing, what it's saying is that it's building upon each other. And it's saying that future errors are based upon past errors, that they're building, and we don't want that. That's a problem. And so if we see this shape in our data, it's telling us that future errors are based on past errors and that we actually have an issue.
Sorry, can you put the paper a little bit up?
I can. So we don't want to see that shape when we plot our residuals against predicted. If what we're predicting and what we're seeing, almost like in chi-square, right? What you're predicting, what you're seeing, if they're different and they're actually going away from each other, we got some problems. Okay. And so those are assumptions for our regression. So far, so good. Those are our assumptions for our regression. So when it's simple regression, it's pretty easy. When it's simple regression, it's pretty easy, right? We can see the slope, the intercept, and based off of the slope and the intercept, we're good, right? We can forecast things out. If we have a y and an x, and it's just simply put a line in there like that, we're good. But what happens if we put something else in there? Okay, well, what happens if we then, as we're increasing breathing treatments, we're decreasing time, what happens if we have something else that we put in there in the mix? Another treatment. How about antibiotics? As antibiotics increases, this is antibiotics, so that's one variable. Just so B1 and B2. So maybe B2 is antibiotics because this is breathing treatment. As we increase antibiotics, it then increases or decreases the amount of days that we're spending. So this is antibiotics, and this one is breathing treatments. Okay. And then maybe we have something else that we put in there that we notice that, so we have antibiotics, we have breathing treatments, we put something else in there like possibly some type of new experimental medication.
There's something that they're giving people now. It's like to fight the virus.
Yep. And they're experimenting with it. It's not been proven yet, but we have this new experimental medication.
It says that it's supposed to be like fight 84% of
So there's a new medication that they say that fights 84%, I'm told. And so imagine as we increase these pills, right? So as they take the pills, so if they take the pill, it increases it. So dummy variable, either they take it, they don't. And if they do, it increases it by 84% or decreases the stay. Okay. So here we have a dummy variable. They take it and it decreases the time exponentially. Some type of medication. Okay. And we have all these variables. And now we're trying to solve the amount of time they're going to stay based off of the intercept plus B1 plus B2 plus B3 plus or minus the standard error. Okay, so we're trying to solve that to figure it out, but we need B0. We can't just simply go off this one and say that's going to be it for all of them, because if we did that, then all the other lines would be curvilinear. So we need to try to figure out like how we can come up with an intercept that stays with, that keeps all these slopes constant with those numbers. And so we can just kind of move them around, but we can adjust them a little bit as long as we're within their standard error to come up with an intercept. And so if we do come up with an intercept and we say, okay, you know, possibly it's right here. And so we take this line and we just move it up a little bit. We take this line, we just kind of move it down a little bit. And we take this line and we kind of, in order to make it fit, we got to kind of straighten it out a little bit. And then we come up with this intercept. We've now kind of changed the values of these lines just a little bit in order to come up with the intercept, right? These calculations are quite complex, so I'm kind of simplifying it here, but now we have a lot more error in our model, or potentially do. And so we need to run these tests and we need to say, okay, well, how strongly correlated are these? What's taking place in there? How much does it really affect it? And so we're now going to constantly needing to be checking our R-square every time we run different models to see how good the fit is. And so these other numbers now become essential. And now after we've changed these slopes, we really need to make sure that we've not created curvilinear lines. We really need to make sure that we've not created too much dependency in this and that our standard error is okay, that there's not too much error in the model. We really need to make sure that now, because we've changed our data and we've kind of manipulated our samples, that our skewness and kurtosis is still okay and that we're equally variable, right? We need to check that because we've actually manipulated some of these points. And so when we start looking at our regression now we have this intercept, right? Where it's a line like this, and we've moved another line that's like this, and maybe another line that's now like that, and they all intersect there. And if I call that B1, B2, and B3. Okay. Now, initially here, they all had a nice slope to it. But now when we look at this one, is that now too flat to be a slope? I don't know, but we need to check it. So it kind of adds another thing into the mix. Because if it's now too flat to be a slope, maybe we have to remove it. Even though it could be like something that's useful. So we just got to be careful because that intercept is what screws us up, right? And if it's a new medication, then what do? Right? Perhaps we remove one of the other variables, or we can do an interactive term to see if we can fix it, right? But it definitely creates some issues, and that's where the issues for the regression model come into play. So now let's take a look at a regression model And let's look at all the stuff and how they all come into play and how they all work together in order to understand how increasing or decreasing these treatments will either increase or decrease the stay in the hospital, right? Because we may find out that this new medication, we give it to some people and they have allergic reaction and their time increases, right? Or we may find out that it doesn't work on people with diabetes, or it doesn't work on people with heart conditions, but on completely healthy people it does. So we may learn that it's curvilinear, or it may work on everybody. I don't know. But we need to check that, because we can't just recklessly give it to everybody and end up like killing a large population. We need to find out like what are the parameters for it. We may find out, hey, it only works on younger people, or it only works on older people, or it doesn't work with people with diabetes, or that type of stuff. We need to find that out before we release it to all the public. Otherwise, we can have a nightmare. And so let's now look at multiple regression sample and see if we can make heads or tails of it. Okay, so I'm going to go back to our La Lima, and I'm going to go to our Excel note files, and I'm going to look at our chapter 13. Let me see if I can find one here. Even though that one is nursing. Get rid of that. Okay, we can use this one. So I'm going to use, if you go to Excel note files, it's 13.34A. 13.34A. And we're going to adjust that to make sense of it, okay, for our case. And just follow through with the same one that we're looking at. Okay, so here we're looking at the amount of hours somebody is staying in a hospital. And based off of the amount of hours somebody is staying in the hospital, let me look at the data. Oh, that one's not going to work. Okay, so let's change it to how much an insurance company has to pay for each person that it's in the hospital, and looking at the treatments, and what they're trying to do is to save some money. So should they use these different treatments? No. Screen closed. Let me keep the same. I want to keep the same theme. So I'm going to manipulate the data to make it work for us. Okay. Give me just a second. We're going to look at the age of the people. And if that's a good measure, so the age of the people, the medicine they're taking, got it. So I just wanted to custom make one for us to keep us on track with the same thing, to understand it rather than to change to something else. Okay. So sorry I took that time, but I wanted to take that time in order to fix this. Otherwise, it won't make sense when we're doing this. Okay, hang on.